Hi everybody, this project group is the Energy Harvesting Pressure Plate, and who we have presenting today is Logan, Jared, Greg, and my name's Jack. Here we go. The main question we're trying to answer with this project is how much power can piezoelectric transducers generate, and can they realistically be used as a power source for small appliances? We want to explore if this technology uh, could provide a renewable, low-waste alternative to batteries for things such as keyboards, controllers, or small lights. To investigate this, our objective was to measure how different numbers of piezoelectric transducers respond to varying energy inputs. We ran drop tests using 3 different weights and drop heights and recorded the voltage for single, double, and quad transducer configurations. This allowed us to evaluate the relationship between input energy and output voltage and compare the efficiency of each configuration. This project aims to use piezoelectric transducers to generate electricity from mechanical impacts. By dropping weights onto different transducer configurations such as single, double, and quad, we were able to measure the output voltage of each. We decided to downscale our project because of the time constraint and the complexity of what we originally wanted to do, which was to build a full uh, pressure plate that someone would be able to step on. We realized that making an entire pressure plate would not be a realistic goal to have accomplished by the end of the semester. However, we did test similar concepts that we had for the project just on a smaller scale by only testing the output voltage on a single, double, and quad transducer configuration. And the significance of this project is that testing this device could prove to be a viable way to recharge some devices such as keyboards, controllers, or even light bulbs. When transducers are impacted with a mechanical force, the impact it can have is that it can create a new type of renewable energy that doesn't create any waste while also having the potential to save the consumer money by not having them spend more on batteries for their devices.
For our experiment, we decided to collect our data through drop testing. For testing, we built a circuit that when a weight was dropped on a transducer, it would supply power to the circuit. The circuit was also connected to a PC in the lab that stored all of the data into NIMax. For testing, we had 3 configurations for the transducers. First, we had the single, the double, and then the quad. We had a mechanical arm holding a drop tube that guided our weights into the center of the transducer to get the most accurate hit for all of them. We used 3 weights for this. We used an 8, a 10, and a 20-gram weight. Our weights were sinkers. We dropped these weights from 12 inches, 8 inches, and 4 inches. For actually collecting the data itself, we wrote the MATLAB code that you can see on this slide with the help of Professor Hoover. We found for this code you can set the duration to collect data at whatever rate you want. For ours, we found 15 to 20 seconds to be enough for 5 drops at each height for each transducer configuration. Through collecting this data, we brought in, I believe, to be around 130 total points. The results from this data can be seen on the next slide and will be discussed by our group leader, Greg.
So for equipment and costs, most of our equipment was provided by the school. The only part that wasn't was the transducers, but they were very inexpensive. It came out to about $22, and that was all we had to pay for. Everything else here was either provided by us or the school. So for our scheduling, we did kind of go off track a little bit. We did purchase our transducers around the 10th or 11th, I want to say. It was one of those days. But they took a lot longer to come in than we thought, so we didn't wait for them to start our construction. We just went ahead and did our construction. Um, Construction took a couple extra days, I think. We were having a lot of trouble with our rectifier and our capacitor, but we got it all figured out. And then we finally got the transducers in, and then our testing did not take as long as we thought it was going to take. I think we did our testing from April 25th to April 27th, so we did not need a full 9, 10 days to do the testing. And then after we finished all of our testing, we started doing our data analysis.
As mentioned in the prior slides, the different test variables that we're testing and collecting data on were transducer configurations, different masses, and different drop heights. We also recorded peak voltages and peak power outputs for each variable. This here is a summary of our data. It shows average voltage output and power from each type of configurations from each test parameter. It also gives a 95% confidence interval based on the 5 repeated tests per parameter for both voltage and power. Later we will discuss that height has a slightly greater impact than mass. So to make things a little simpler for this presentation, I went with presenting the drop heights versus voltage and power outputs. This graph here shows average output versus height. Error bars were made using 95% confidence interval, revealing that the quad transducer configuration was inconsistent and the single load transducers were very consistent. We see that the R squared values are relatively close to 1, showing that as we increase height, the average voltage output generally increases linearly. Similar to last slide, I wanted to keep things a little bit more streamlined, so I decided to go with power output versus drop height. We calculated average power using P equals voltage average squared divided by the resistance, which happened to be 10 ohms. As we see increased height, we also see a relatively linear increased power output, an R square valued of 0.978. This section is where the majority of our data analysis comes from. Using ChatGPT, I was able to come up with some Python code to help me perform a three-way ANOVA test. A three-way ANOVA test basically just compares, or it evaluates 3 independent variables and their impact on a continuous dependent variable. It gives us both an f-stat value and a p-value to help show significance. Below here we can see that the transducer had a significantly high f-stat value and a p-stat value of way less than 0.001. Height then follows with a significantly smaller impact, and then mass ends it off having the least amount of impact. After performing the three-way ANOVA test, I then performed an honestly significant difference Tukey test on all 3 parameters to further prove significance on output. A Tukey test basically compares which group means are significantly different from each other and gives us a p-value for each respective category. This one describes mass. We got a p-value of much bigger than 0.05, meaning that realistically speaking, mass has little effect on overall output. The relatively large error bars in this graph could likely be from either high variance with little voltage differences or just the relatively small sample size that we took. Similar to the last slide, height also doesn't have a huge impact on output. We got slightly thicker bars here with a p-value of still over 0.05. Relative large error bars, again, same thing as last time, high variance, little voltage difference, and small sample sizes. This slide shows a Tukey comparison. Here we can see that there's much more impact than both mass and height. We have large bars showing that our p-value is much smaller than 0.05. We have relatively small error because lower standard deviation. Lastly, we performed an uncertainty test using 95% confidence intervals. This also includes standard deviation. We can see here that load single had the most consistent output while having the least amount of overall output. Error is color-coded red, with red being high. We can see that most of the error is actually corresponded with our quad configuration, which makes most sense as the variance for that was all over the place. We can see that variability decreases as height increases. Just to recap, we generally see that when we increase the height, the output voltage and power also increased. We see that the single and double transducer configuration had the best output. Mass had the least effect on output, whereas transducer configuration had the most effect on output, with ANOVA test values of F over 1000 and P significantly smaller than 0.001. Results generally followed a predicted trend, and we have small sample size and high variance, so this causes a higher standard error. Now I'll pass it on to Logan to go for conclusion.
So for the conclusions, we had a couple things that we wanted to put on here. The first was the uncertainty in voltage increases as the number of transducers increase. As you can see in our results probably, we had a significant increase in uncertainty with the 2 and the 4 compared to the 1 transducer tests. I think that has a lot to do with the material we use, but also hitting the direct middle of all of the transducers as well. We were kind of off on some of them. I tried to get it as perfect as possible, but some of the drops didn't land directly in the middle. I think that caused a lot of the uncertainty. Um, the height didn't really affect the voltage output as much as we thought. And also adding the load resistor to our circuit, it significantly decreased our voltage output, but it also made our tests extremely consistent. We had a very low standard deviation when using a load resistor, which could be favorable in some real world scenarios. Um, and we concluded that our first objective with the energy harvesting pressure plate was not feasible with the amount of wattage that we were producing. We were not getting anywhere close to enough power to be able to sustain a battery in a energy harvesting pressure plate. So finally, for future work, we have implementing a battery charging system into our experiment. We couldn't do this with the project time limit for this semester, but I think it would be something to look forward to into the future. Um, Next is looking into different uses in the real world for our system. So the energy pressure plate probably isn't going to be a viable source, as I said before, but we're looking into putting our system into a keyboard. So as when you tap on when you're tapping on your keys, it's creating a small amount of wattage, but over time, if you're tapping enough on your keyboard, it'll just automatically charge your keyboard and you won't have to recharge your Bluetooth keyboard. So I think that would be a very cool implementation into the real world. I think it would work. I've looked online. There's not really any rechargeable Bluetooth keyboards that none of them that use the piezoelectric transducers, but there's some that do solar charging, and it doesn't seem to be a mass market thing. It's very limited, and they seem very expensive as well. So I think implementing it into a keyboard would be a great option, and I think it would actually do well in the real world. More future work is using different, more reliable transducers. Our transducers were really cheap, just right off Amazon. I think we paid about $20 for 20 of them, so they were not expensive at all. But if we wanted to implement our project into a keyboard, we'd have to get more reliable and more consistent transducers. But the problem is those are very expensive, so we were looking online before the project at transducers. And some of them were over $100 for bendable ones and stuff like that. So that'd be something to look into for a future experiment with the transducers. So yeah, that's our project.